Hello students, welcome to the session. In our previous video, we have discussed how to evaluate the line integral for a given curve C. Whenever a given curve C consists of two or more subpaths, then the evaluation of line integral becomes tedious. In that case, we can use some of the integral theorems by using which we can evaluate the line integral easily. In this section, we are supposed to study three important integral theorems. One is called Green's theorem in a plane, one is called Stokes theorem, and one more is called as Gauss divergence theorem. Now, let us concentrate on the first one, that is the Green's theorem in a plane. And this Green's theorem establishes the relation between the line integral and that of the double integral over a region R. And that's why we can say that Green's theorem gives a relation between the double integral over the region R in xy plane and the line integral over a closed curve C enclosing the region R. It helps to evaluate the line integral easily. Means using Green's theorem, we can easily evaluate the line integral whenever it seems to be tedious with the usual way of evaluating line integral. Now let us concentrate on the statement. Let m of xy and n of xy be two functions defined in a region R. Okay, this is a region R, and two functions m and n are defined in this one, which are the functions of x and y in xy plane with a simple closed curve C as its boundaries. Therefore, the boundaries of the region R is taken as a closed curve C. Then the Green's theorem in a plane states that the line integral over the closed curve C of m dx plus n dy equals to double integration over the region R dou n by dou x minus dou m by dou y into dy dx. Therefore, now this is the double integral over the region R of dou n by dou x minus dou m by dou y into dy dx, means where dou n by dou x is the partial derivative of n with respect to x and dou m by dou y is the partial derivative of m with respect to y. Now let us see how this Green's theorem in a plane helps to evaluate the line integral easily. And proof is beyond the scope of the syllabus. Just we supposed to use the statement of the theorem and we go for concentrate on the examples. Now let us consider examples on that Green's theorem. Now the first example says, verify Green's theorem for integration over the closed curve C xy plus y square into dx plus x square into dy, where C is a closed curve bounded by the line y equal to x and the parabola y equal to x square. Now, just by the practice we can say like that, but let us analyze how it is. Once you compare the given line integral with the LHS of Green's theorem, we can find that in the place of m, okay, we are finding xy plus y square. That's why here we have that is m equal to xy plus y square and n equal to coefficient of dy, that is equals to n square. Now, once you look at the RHS, we need two things, that is a partial derivative of n with respect to x and partial derivative of n with respect to y. First, let us concentrate on the finding the partial derivative of m with respect to y. Once you differentiate with respect to y, x is a constant, y with respect to y is 1, plus derivative of y square is 2y. And the partial derivative of n with respect to x is, the derivative of x square with respect to x is 2x. Now, first let us identify the region in the xy plane. Okay, first let us concentrate on the first curve, that is y equal to x. Therefore, y equal to x is a straight line passing through the origin, and y equal to x square. Okay, this is another curve which represents a parabola which open upwards. Therefore, y equal to x square is a parabola which open upwards, and y equal to x is a straight line which passes through the origin. Therefore, this shaded area will be area bounded by the given two curves. Okay, and the path, closed path is, that is O, A, O. That will be your closed path. That is C, what we can call. Okay, now first let us say at the point of intersection where the two curves intersect. Now let us solve equation y equal to x and y equal to x square. Since LHS are same, once you equate RHS, we find x equal to x square. Taking this x on another side and by factorizing and solving, we get x equal to 0 and x equal to 1. Accordingly, we get y equal to 0 and y equal to 1 because one of the equations says y equal to x. And therefore, one point of intersection is 0, 0, that is origin, and one more point of intersection is 1, 1, that is this point. Therefore, these are the 2 points of intersection we find. Now, let us concentrate on LHS, that is integration over C, that is m dx plus n dy. But the curve C, what we call it as a closed path, now it consists of 2 subpaths. One is OA, another is AO. That's why we can write this one as the same integration over the one subpath OA plus the same integral over another subpath, that is AO. That is, let us take this integral as I1, let us take this integral as I2. Now, once we concentrate first integral, that is along OA, first of all, you have to identify what is the curve. OA, this refers to the curve y equal to x square. Therefore, y equal to x square, because OA is a curve belongs to, or it is a part of the curve y equal to x square. Therefore, the equation of OA we can take it as y equal to x square. This implies dy equal to 2x dx. And here, the variation for x is, that is here x is 0. When it reaches here, the x value is 0 here and x value is 1. That's why here we can write x varies from 0 to 1. Therefore, I1, what is I1? That is integration over OA m dx plus n dy, but m is, we have already written, that is xy plus y square. Okay, xy plus y square into dx plus, okay, that is another one is n is x square into dy. But according to the curve OA, we have y equal to x square. Wherever y is there, let us take x square, and wherever dy is there, let us take 2x dx. Once you substitute y equal to x square, that becomes x into x square plus y square means x square square, that is x raised to 4 into dx plus x square as it is. Dy is 2x dx, and here x varies from 0 to 1. Now x varies from 0 to 1. If I take dx as my common term, then we find here that is x cube plus x raised to 4, and here it is 2x cube we find. That is 2x cube plus x cube, that is 3x cube. Once we integrate with respect to x, 3 as it is, x cube with respect to x is x raised to 4 by 4, plus integration of x raised to 4 is x raised to 5 by 5, and you have to take the limit from 0 to 1. Once you take the upper limit, we find it as 3 by 4 plus 1 by 5, minus with lower limit both reduces to 0. Therefore, if you take 20 as LCM, that is 4 5s are 5 4s are, that is 15 plus 4, that is 19 by 20. Therefore, that is the value of I1, or the integration over the along the curve OA. Now we have to find one more, that is along I2, that is along AO. Earlier we evaluated along OA, now we have to evaluate along AO now. Now AO is a curve which corresponds to the line y equal to x. Therefore, this implies dy equal to dx. And here the value of x is 1. When we reach here, the value of x becomes 0. That's why we can write here x varies from 1 to 0. Therefore, I2 can be written as integration along AO, that is m dx plus n dy. Actually, m is nothing but, we already written m is nothing but xy plus y square. But in this case, that AO corresponds to the curve y equal to x. Therefore, wherever y is there, let us take x, and wherever dy is there, let us take dx. If we do so, that becomes x into x plus x square into dx plus x square as it is, dy is dx. And if you take dx as common term, here x square plus x square plus x square will have, that is 3x square. If you integrate by keeping 3 as it is, x cube by 3, it will get cancelled, x varies from 0 to 1. If you take upper limit, its value is 0, and if you take lower limit, it becomes minus 1. Upper limit minus lower limit, that is 1. The simplification leads to minus 1. Therefore, the value of I2 means evaluation of the integral along the path AO, that gives you the value minus 1. Therefore, now I want LHS. LHS is the addition of I1 and I2 according to equation 1. Therefore, we can write 1 reduces to, that is LHS equal to I1 plus I2, that is 19 by 20 minus 1, that is minus 1 by 20. That is LHS. Now the question is verify Stokes theorem. Yes, we have evaluated LHS. Now we have to evaluate RHS, and RHS must also leads the value minus 1 by 20. Okay, now once you look at this one, this is the region bounded by the two curves, that is y equal to x square and y equal to x. Now we have to evaluate this region using double integration, and we know how to evaluate double integration in the first semester. And here we can consider strip parallel to either x-axis or y-axis. If we consider the strip first parallel to y-axis, then the order of the integration is dy dx. If we consider a strip parallel to x-axis, then the order of integration is dx dy. Here we have taken the strip parallel to y-axis. Therefore, let us write that is dy dx. Okay, and see here first that is r. Let us take that one as r itself. First n with respect to x. We already calculated n with respect to x is 2x. That we have written 2x minus m with respect to y. That is x plus 2y. It is minus of x plus 2y dy dx. Since you have written the order as dy dx, first let us set the limits for y. Now looking at this diagram, you take any point on this curve, okay, y value is x square. When you reach here, you take any point on this line, y value is x. Therefore, the variation of y is, that is x square to x. That we have written the variation for y as x square to x. Now this strip has to start its journey at this point. It has to end its journey at this point. And in that region, here x equals to 0 and here x equals to 1. That's why the strip has to start its journey from the point x equals to 0, and it has to end its point at x equals to 1. Therefore, if you take like that, here you say that is x equal to 0 to 1 with this dou n by dou x minus dou n by dou y. The simplification is 2x minus x is x minus 2y. First, let us integrate with respect to y. We will get xy minus y square. Taking the limit as y square equal to y equal to x square to x, we get, first to take the upper limit now, that is x into x, that is x square, minus lower limit, that is first x into x, that is x square, and we take y equal to x, that becomes y x square, minus upper limit is over. Now take the lower limit. Wherever y is there, you take x square, that is x square into x, that becomes x cube, minus x square square, that becomes x raised to 4 into dx. Now x varies from 0 to 1. These two will get cancels, that becomes x raised to 4 minus x cube with respect to x. X raised to 4 with respect to x is x raised to 5 by 5 minus x cube with respect to x is x raised to 4 by 4 for the limit 0 to 1. And the simplification is, if you take the upper limit, that is 1 by 5 minus 1 by 4, lower limit reduces to 0. The simplification leads to minus 1 by 20. Therefore, once you evaluate LHS, that gives you minus 1 by 20. And once you evaluate RHS, then also its value is minus 1 by 20. Once you look at this, here there are only two subpaths. That's why that integral has to be evaluated twice by calling one as I1, one more as I2. Whenever the number of subpaths in a closed curve, okay, will go on increase, accordingly the evaluation process also becomes tedious or time consuming. Therefore, once you use RHS without much difficulty, the same thing can be easily evaluated. That's why we said that the Green's theorem established the relation between line integral and that of double integral for the region R. And using this Green's theorem, easily we can evaluate the line integral in a better manner. That's why in this case we have calculated LHS separately as well as RHS separately. Both leads to minus 1 by 20. Hence we can conclude that Green's theorem is verified. That's the process. Now let us go to the second example. Using Green's theorem, evaluate integration over the closed curve C 3x square minus 8y square into dx plus 4y minus 6xy into dy, where C is the boundary of the region enclosed by the curve y equal to root x and y equal to x square. Okay, now let us denote the given integral as I. Now, once you compare this one with Green's theorem with LHS, we find that Green's theorem, LHS of Green's theorem is integration over a closed curve m dx plus n dy. M is the coefficient of dx, n is the coefficient of dy. That's why we can write m equal to 3x square minus 8y square and n equal to 4y minus 6xy. And the partial derivative of m with respect to y is minus 16y, because we have to treat x constant, this goes 0 and this is minus 16y, and partial derivative of m with respect to x, treat y as constant, this will be 0, that becomes minus 6y. Now the RHS of Green's theorem requires the difference of partial derivative of m with respect to x and that of partial derivative of I think this is m with respect to y. Therefore, partial derivative of m with respect to x is minus 6y minus partial derivative of m with respect to y is minus 16y. It should be m, not n. Therefore, the simplification relates to 10y. Now, let us identify the curve because we need the path or a closed region we need. That's why let us analyze what are the curves given. Y equal to root x. Here we cannot conclude what is the curve. Okay, now to get what is that curve, let us squaring on both sides, we get y square equal to x. This is of the form y square equal to kx. Therefore, this is a parabola which open right side. And y equal to x square. Straight away we can claim x square equal to y. Again, it is also a parabola which open upwards. Now, in order to know where they intersect, now let us solve equation 1 and 2. Therefore, here it is y square is there, but according to the second equation, we have that y equal to x square. If you substitute, that becomes x square square equal to x. Therefore, that becomes x raised to 4 minus x equal to 0. If you take x as a common term, that becomes x cube minus 1 equals to 0. That indicates one is x equal to 0 and one is x equals to 1. I think this will be 1. It's not 0. Accordingly, we find, because when you equate this one to 0, okay, we get x equal to 0. And we equate this one to 0, sorry, this one to 0, we get x equals to 1. It is 1. It's not 0. Therefore, accordingly, we find y equal to 0 and y equal to 1. Because once you take the value of x here as 0, we get y equal to 0. Once you take x equals to 1 here, we get y equals to 1. Now, by Green's theorem, okay, how we can evaluate the line integral? That's why we say by Green's theorem we have, that is integration over the closed curve C m dx plus n dy equals to double integration over R, that is dou n by dou x minus dou n by dou y dy dx. Therefore, one curve is y square equal to x and one more curve is y equal to x square. Therefore, this is the closed region what we can say. Now, if I want to go traditionally with LHS, I have to evaluate the integral over two subcurves. One is OA and one is AO. Rather than that, if you go with RHS, we can claim that it is double integration over the region R, dou n by dou x minus dou n by dou y dy dx. That's right. This is the LHS equals to double integration over R, and we find the difference, that is dou n by dou y minus dou n by dou n by dou x minus dou n by dou y equal to 10y, that we have taken dy dx. Now double integration over R. Now we have to evaluate this integral over this region. Okay, now for that, let us consider strip parallel to y-axis, and we have to set the limits first for y, and this is the lower curve corresponds to y equal to x square. When you reach here, we get y equal to root x. That's why the limits for y are x square to root x, then is a constant is taken out. And now to cover this region, this strip has to start its journey at this point and it has to terminate its journey at this end. Therefore, when it starts its journey, the x value is 0. When it reaches here, the x value is 1. That's why we can write x varies from 0 to 1. That's why this is 10. Integration we kept as it is. Y with respect to y is y squared by 2 over the limit x squared to x dx. Therefore, it is 10 by 2. If we take upper limit, that becomes x square minus lower limit x raised to square. That becomes x raised to 4 into dx. Therefore, it is 5 times. If we integrate x square by 2 minus x raised to 5 by 5, by taking upper limit minus lower limit, we get it as 5 into 1 by 2 minus 1 by 5. If we simplify, it leads to 3 by 2. That will be the value of the line integral which is evaluated over the closed path bounded by the curves y equal to given root x and y equal to x. Let us go with one more example. That statement is like this. Using Green's theorem, evaluate the line integral over the closed curve C, x square plus xy into dx plus x square plus y square into dy, where C is a square formed by the lines that is x equals to plus or minus 1 and y equal to plus or minus 1. Once we know or once we compare the given line integral with LHS of the Green's theorem, we find m as coefficient of dx, that is x square plus xy, and n as coefficient of dy, that is x square plus y square. Now we need the partial derivative of m with respect to y. That's why x to be treated as constant, this becomes 0, x as it is, y with respect to y is 1. And one more, n with respect to x. Now when you are finding partial derivative of n with respect to x, you have to treat y as constant. When you treat y as constant, this becomes 0, this gives you 2x. Now you have to take the difference between partial derivative of n with respect to x and that of m with respect to y. That gives 2x minus x, that one equals to x. Now first let us identify the closed region. They are given 4 lines. One is x equal to plus or minus 1, that is x equal to plus 1 and x equals to minus 1. These are the 2 lines. And y equal to plus 1 and y equal to minus 1. The shaded area will decide the boundaries of the closed region. Okay, now by Green's theorem we have, that is the integration over the closed curve C m dx plus n dy equals to double integration over r m with respect to x minus m with respect to y dy dx. Now in order to cover this region, I will consider a strip parallel to y-axis. First let us set the limits for y. Therefore y varies from minus 1 to plus 1. Okay, and this strip has to start its journey from this line and it has to end its journey with this line to cover entire region. That's why x varies from minus 1 to plus 1. Now we already computed the partial derivative of m with respect to x minus m with respect to y, that is x. It has to be integrated first with respect to y over this limit, then with respect to x over these limits. X will keep as it is. Now integration of dy is y, that is over the limit minus 1 to plus 1 into dx, that is integration x varies from minus 1 to plus 1, x as it is, upper limit minus lower limit means that becomes 2. I'll take 2 as outside. Now x with respect to x is x square by 2. These two will get cancels for the limit minus 1 to plus 1. If we take the upper limit, it gives you 1, minus if you take the lower limit, that is minus 1 square is again 1. 1 minus 1 equals to 0. That's why the value of this line integral for this closed curve is going to be 0. Now let us go to one more, that is using Green's theorem, evaluate the integration of the closed curve C to x square minus y square into dx plus x square plus y square into dy, where C is a triangle formed by the lines y equal to 0, x equal to 0 and x plus y equals to 1. Once you compare with the LHS of Green's theorem, we find m equal to 2x square minus y square and n equal to x square plus y square. And the partial derivative of m with respect to y as minus 2y and the partial derivative of n with respect to x is 2x. If you take the difference between partial derivative of n with respect to x and that of m with respect to y, it results in 2 into x plus y. Now by recalling Green's theorem, we can write like this. First, let us know what is that closed region. Okay, and they are given y equal to 0, that is x-axis, x equal to 0, that is y-axis, and x plus y, this is a line, that is x plus y equals to 1. Because if you take x equals to 0, we get y equal to 1, this is point. And if you take y equal to 0, then we get x equals to 1, therefore this is another point. By putting those 2 points and joining these 2 points, we get this is a triangle. Okay, now by Green's theorem we can write like this. Now again this is the region bounded by these curves. In order to cover this region, I'll consider strip parallel to y-axis. First let us set the limits for y. Y varies. You take any point on this line, y value is 0. And if you take any point on this line, y value is 1 minus x. That's why y varies from 0 to 1 minus x. Now in order to cover this region, this strip has to start its journey at this line and it has to end the journey from this point. At this line x equals to 0, where it reaches here, the x value is 1. That's why x varies from 0 to 1. Now, if we evaluate this one, 2 is a constant, I'll take it outside. First, let us integrate with respect to x now. Sorry, y. That is integration of x with respect to y is xy. Y with respect to is y square by 2. Take the limit from 0 to 1 minus x. 2 as it is. That is, first let us take the upper limit. It is x into 1 minus x plus 1 minus x whole square divided by 2. And with lower limit, both comes to 0. The resulting has to be integrated with respect to x. 2 as it is, this becomes x minus x square plus 1 plus x square minus 2x by 2. If we take totally 2 as LCM, this 2 will get cancels with this 2 as we have written here. You have to multiply these two terms by 2, that gives you 2x minus 2x square plus 1 plus x square minus 2x with respect to x. Therefore, this 2x will get cancels. That is 1. X square minus 2x square is minus x square. It has to be integrated with respect to x. 1 with respect to x is x. Minus x square with respect to x is x cubed by 3. For the limit 0 to 1. If we take the upper limit, that becomes 1 minus 1 by 3. With lower limit, both terms to 0. That is 0. That is simplification. This one is 2 by 3. Therefore, the value of the line integral for the closed curve C, which is bounded by the curves y equal to 0, y equal to x, and x plus y equals to 1, is given by 2 by 3. That's the required value. Now, let us go with one more, which is appeared in the model question paper. And the statement of the problem is like this. Using Green's theorem, evaluate integration over the closed curve C, x square plus y square into dx equal plus 3x square y into dy, where C is a circle, x square plus y square equal to 4, traced in the positive sense. Therefore, the curve x square plus y square equal to 4 is a circle with center at the origin and radius 2. Radius 2 means here at this point is minus 2 to plus 2, and that is the reason, or circle we can say. Once you compare with the LHS of the Green's theorem, the coefficient of dx is m, that is x square plus y square. The coefficient of dy is m, that is 3x square y. Now the partial derivative of m with respect to y is 2y, and the partial derivative of m with respect to x is 6xy. Their difference leads to, that is, if you take 2y as the constant term, that becomes 3x minus 1 into 2y. And C is a circle, therefore x square plus y square equal to 4. Accordingly, we can write y equal to plus or minus square root of 4 minus x square. Okay, now once you go with this one, to cover this reason, let us consider straight parallel to y-axis. At this point, the value of y, you take any point in this region, the value of y is minus square root of 4 minus x square. Minus sign is because it lies in the fourth quadrant. Here it is plus because it lies in the first quadrant. That's why y varies from minus square root of 4 minus x square to square root of 4 minus x square, and x varies here. In order to cover this reason, this line or this strip has to start its journey at this point and it has to end its journey at this point. At this point, x is minus 2. At this point, x is plus 2. Okay, that we have written as a limits for y and x. Now, taking 2 as a constant outside, keep a 3x minus 1 as it is independent of y. Therefore, y with respect to y is y square by 2 over this limit, and the resulting has to be integrated with respect to x. This we kept as it is. To take the upper limit, that is becomes after cancellation of the square root, we get this minus. Again, this becomes 4 minus x square. This will get cancelled 0 into something, that is 0. Therefore, the value of the integral becomes 0. Okay, these are the basic examples or standard examples on how to use Green's theorem to evaluate the line integral in a more simplest way as compared to the usual way of proceeding with LHS. Now, and one of the important application of Green's theorem is it can be used to find the area bounded by the curves. Okay, how we can find the area bounded by the curve using Green's theorem? Let us discuss that. So finding area using Green's theorem. By Green's theorem, we have the statement like this. Wherever m is there, let us take minus y. Wherever n is there, let us take x. Partial derivative of m with respect to y gives minus 1, and partial derivative of m with respect to x is 1. Therefore, if you take this one, that is integration of the closed curve C, m is minus y and n is x. That is minus y into dx plus x into dy. Double integration over r, and this difference becomes 1, minus of minus becomes plus dy dx. That is 2 times double integration over r dy dx. And double integration over r dy dx, that represents area bounded by the region r. That's why we can write this one as 2 times area of the region R. But we want the area of the region R. Okay, that's why this 2 has to be cross multiplied. That's why area equals to 1 by 2 times. After cross multiplying, that will be here. First, let us write the positive term, that is x into dy minus y into dx. Therefore, this is the formula which is derived from Green's theorem just by taking the particular values for m and n as m equal to minus y and n equal to x. This can be used to find the area bounded by the curves. Now let us go with a simple example, that is find the area of the ellipse x square plus x square by a square plus y square by b square equals to 1 using Green's theorem. Okay, and this is the ellipse, and the parametric equation of the ellipse are x equal to a cos square a cos theta and y equal to b sin theta, and the variation for theta varies from 0 to 2 pi. That is variation is 0 to 360 degree. Therefore, as we taken x equals to a cos theta, dx results as minus a sin theta d theta, and dy results b cos theta d theta. Then by Green's theorem we have, that is area is given by 1 by 2 times integration of the closed curve C x dy minus y dx. That is here the parameter is theta we have taken, that is theta varies from 0 to 2 pi, x equals to a cos theta, and dy is b cos theta d theta minus y is there, y is b sin theta, and dy is what you can say dx, sorry, not dy, dx is minus a sin theta d theta. Just let us substitute the values of x, y, dx, dy from these above steps. We are going to get this one. And here also we get ab, here also we get ab, that ab is taken out. Here cos theta into cos theta, that is cos square theta, minus of minus becomes plus, that gives us sin square theta after taking d theta as common term. Therefore, this is ab by 2 that we can take outside. And we know cos square plus sin square is 1. And the integration of 1 with respect to theta is theta. And we have to take the limit from 0 to 2 pi. This is ab by 2 we have. Take the upper limit, that is 2 pi minus lower limit 0. 2 will get cancelled, that will be pi ab. Okay, and in our lower classes also we have studied with a single integration that the area of the ellipse is computed as pi ab. Using the Green's theorem concept also we can get the area of the ellipse as pi ab in this particular way. Therefore, this is the formula we have to remember to find the area bounded by the curves using Green's theorem. That is, area is given by 1 by 2 times integration for the closed curve C, that is x dy minus y dx. That's the formula we have to remember to find the area bounded by the curves using Green's theorem. Now this is one important example which appeared many of the times in the examination also, and the question like this: find the area between the parabolas x square equal to 4y and y square equal to 4x using Green's theorem. That is y square equal to 4x, which is a parabola which opened right side, and x square equal to 4y is a parabola which open upwards. Now this is y square equal to 4x, and this is x square equal to 4y. Now in order to get the point of intersection, let us solve these two curves. From the second curve we find the value of y as x square by 4. Taking that value in the first equation, we can write like this. And once you square this one, that becomes x raised to 4 divided by 16 equal to 4x. That gives you x raised to 4 equals to 64x. Taking that on the other side and simplifying, we get this. Equating this one to 0, we get 0. Equating this one to 0, we get x equals to 4. Again, by taking the value of x here, okay, we can get first when you take x equal to 0, we get y equal to 0. If we take x equals to 4, that becomes 16. 16 by 4 is 4. Then we have the point of intersection. One point of intersection is 0, 0, that is here. Another point of intersection is 4 and 4, that is this. Therefore, this area we have to find out. Okay, now this one can be written as integration 1 by 2 times. Okay, that is, let us recall the Green's theorem. Okay, for areas. Okay, it is like this 1 by 2 times. Since this is the region we have to cover, and that region is bounded by two subcurves. One is OA and one is AO. That you are written like this. Okay, first along OA, that is along this curve OA. OA corresponds to the curve x square equal to 4y. Okay, that implies y equal to x square by 4. That implies dy equal to 2x dx by 4. That becomes x by 2 into dx. And here x varies from 0 to 4 along this curve. That's why we written x varies from 0 to 4. And one more, along OA we find x equals to y square by 4. That gives you dx equals to y by 2 into dy. And now when you come from this to this, here y is 4. When you reach here, y is 0. That's why we have written y varies from 4 to 0. Okay, now this using this equation 3 reduces to 1 by 2 times. X varies from 0 to 4. Therefore, x as it is. And from this equation we can write that is y equal to x square by here. That is x dy is there. And dy is dx x dx by 2. That is x dx by 2 minus y is there, but y is x square by 4 into dx. Because along the curve OA, we have converted integral in terms of dx or integral in terms of x. That's why the limits are with respect to x. Along AO, we have converted in terms of y. That's why convert everything in terms of y. According to second curve, x is given by y square by 4. That is y square by 4 into dy minus y as it is, and dx is given by y divided by. Once you go and simplify this one, that is x varies from 0 to 4. That gives you x square by 4, x square by 2 minus x square by 4. We get into dx. And here it is y varies from 4 to 0. It is y square by 4 minus y square by 2 into dy. Therefore, the LCM seems to be simplify this one. This gives you x square by 4. And this gives you minus y square by 4 with respect to y. And here it is with respect to x. Now here also 4 is there, here also 4 is there, 1 in the denominator. Let us take that one. It is 1 by 4 outside. X square with respect to x is x cube by 3 over the limit 0 to 4 minus plus into minus is minus. Integration of y with y square with respect to y is y cube by 3 over the limit 4 to 0. Now it is 1 by 8. Once you take the upper limit, that becomes 64 by 3 with lower limit is 0 minus upper limit 0 minus of 64 by 3. Minus of minus becomes plus, that is 1 upon 8. That gives you 2 into 64 divided by 3. This gives you 8 times 8. It's 8 into 2, that is 16 by 3 square roots. That is the area bounded by the parabolas y square equals to 4x and x square equals to 4y. And this we have evaluated using the help of Green's theorem. This is one important application of Green's theorem. It helps to evaluating the line integral, as well as using Green's theorem one can find the area bounded by the two curves or a single curve. Using the formula, area is given by 1 by 2 times integration over the closed curve C x dy minus y dx. These are some standard examples on Green's theorem and application of Green's theorem to evaluate the line integral as well as to find the area bounded by the curves. Try to evaluate this one example, and the example is like this. Evaluate using Green's theorem, that is integration of the closed curve 2x square minus y square into dx plus x square plus y square into dy, where C is a boundary of the region in xy plane enclosed by x-axis and upper half of the circle x square plus y square equals to a square. Try to evaluate this one. Okay, that is evaluate means only you can calculate RHS of the Green's theorem, so that easily this is your M and this is your N. Try to apply. First you draw the diagram for this scenario and set the first limits for y, then you take the limits for x and evaluate. So you may get the answer as 4a cube divided by 3. Okay, this is all about what is Green's theorem and what are the examples on Green's theorem and how that Green's theorem helps to evaluate the line integral easily. And one more important aspect of Green's theorem is using Green's theorem, we solved one or two examples on how to find the area bounded by the curves. This is all about the Green's theorem. Okay, in our next video, let us concentrate on one more integral theorem that is called as Stokes theorem. There also it helps Stokes theorem, and here the Green's theorem establishes the relation between double integral and that of line integral, and in Stokes theorem it establishes the relation between line integral and that of surface integral. Again, using that Stokes theorem also one can evaluate the line integral easily. That we can study in our next video. Thank you.